So hello everyone, today we are going to discuss NMR spectroscopy. Okay, so it is my first slide in which I have discussed that what is the importance of NMR spectroscopy. So first of all, you should be know about the full name of NMR spectroscopy. So its name is nuclear magnetic resonance. Okay, so there is three terms involved: nuclear, magnetic and resonance. Okay, so there will be need of nucleus of any atom. Okay, magnetic, there is a need of magnetic. Okay, resonance means there will be involved resonance phenomenon. Okay, so first of all, it is very preeminent techniques because it is the only one technique. Okay, so you can, with the help of this, you can analyze the complete analysis and interpretation of any entire spectrum. Okay, so in this larger amount of sample, if you compare from mass spectroscopy, so in this larger amount is needed. Okay, as compared to mass spectrum. Okay, but there is a one benefit: it is non-destructive, means your sample will be non-destructive. Okay, means your sample will be saved after the analysis, and it is modern instrument. Good data may be obtained from sample weighing less than milligram. So to 1 to 3 milligram is sample is required for that analysis. Okay, to be successful in using NMR, first of all your physics or the concept will be clear. Okay, so NMR spectro, since there is need of nucleus, so is nucleus having spins. Okay, so nuclei, there are various types of spins are present. One is the integral spins. The I is equal to 1 to 3 to 3 1 to 3. Okay, fractional spins having I is equal to 1 by 2 means they are nuclei having the spin. Okay, 1 by 2 then will become 3 by 2, then will be 5 by 2. So digits, upper digits will be odd. Okay, few having no spins, I is equal to 0. So carbon having 12, it is the atomic number. Okay, so it is the even. So since it's having even, so even atomic number, so it is the inactive nuclei for the proton spectrum. Okay, or NMR spectrum. Functional nuclei means there is a functional nuclei, or you can say active nuclei. So these are the active nuclei having atomic number even, odd. Okay, and all the having I is equal to 1 by 2. So these are the functional nuclei and required for the NMR spectrum. So come on the NMR spectroscopy, since spinning charge generate a magnetic fields, you should be know about it. Each spin having own magnetic field. Okay, as shown in the animated structure, and in this one external magnetic field is applied. Okay, so when you applied external magnetic field, what happened here? To a one electron having either one having two spin state, plus 1 by 2 and 1 by minus 1 by 2, or you can say it is having alpha spin energy state or beta energy state. But what happened if when you applied external magnetic field, these spins will be differentiated. Okay, differentiated into lower energy state and higher energy state. Okay, so lower energy state is what is plus 1 by 2, and higher energy state is equal to minus 1 by 2. Okay, so in the presence of external magnetic field, two spin state exist, plus 1 by 2 and minus 1 by 2. The magnetic moment of lower energy state is aligned with the external field. Okay, but that of higher energy minus 1 by 2 spin state is opposed to the external field, means the spin having high energy state will opposed to the external magnetic field, while lower energy state, since energy is lower, so that's why what happen here, it will be aligned to the external magnetic field. Okay, so difference in energy between the two spin state is dependent on the external magnetic field strength. Okay, so difference, what I have talked that the difference in energy between the two spin state is dependent on the external magnetic field. Okay, so so these spin state, okay, directly proportional to your external magnetic field strength applied. Okay, and always having very small. The following diagram illustrate the two spin states. So in this diagram I have mentions that. Okay, so come on the third slide. So your magnetic field which is applied, the unit is Tesla. Okay, and each you can say atom for differentiation in spin energy state. Okay, when you then there is a required to 1 to 10 kilocalorie per mole energy. Okay, and these energies applied for mega in megahertz, and 1 megahertz is equal to 10 to the power 6 hertz. Okay, so, okay, and it's ranging to 20 to 900 megahertz. Okay, depending on the magnetic field strength. Okay, so I have discussed earlier. Okay, NMR therefore energetically mildest probe and examine the structure of nucleus molecules. Okay, and magnetic moment of proton, because proton is needed for that, so magnetic moment is equal to 2.79. Okay, so NMR spectroscopy, since if you see here, spin 1 by 2 nuclei, the energy difference between two spin state and given magnetic field strength will be proportional to magnetic moment. Okay, so I have also discussed this point, and in this I have mentioned that these all the atomic nuclei will be active for NMR spectroscopy. Okay, and okay, and okay, it is not important for you, so you can say I have also mentioned in this. Okay, so before discussing this point, this first of all we will discuss the NMR instrument. This is the picture which are taken from the inside of the NMR spectrometer. Okay, so in this if you see this radio frequency transmitter, okay, and radio frequency receiver and amplifier is attached from this part. Okay, this is the NMR tube. Inside the NMR tube, your NMR solvent and your sample is present, which is dissolved in the that solvent. All the solvent needed in deuterated form, because deuterated form will not interact in from your sample. Okay, these are the magnetic field which is applied for giving the magnetic field. Since the atoms having its own spin state. Okay, and magnetic field, and when external magnetic field applied, these will differentiated into spin higher and lower. Okay, and creates the delta E values. Okay, since protons all have the same magnetic moment, we might expect all the hydrogen atoms at the same field. So it is very important point. Fortunately, for chemistry application, this is not true. But what happened? All the compound actually, the protons, since proton are the same, but environment will be the change. Okay, so that's depending on that environment in which your proton will be present, it will affect the chemical shift of that proton. Okay, and it will be arises in different chemical shifts. Okay, so it is not important for you. It is, I have shown that it is external magnetic field applied. This is the induced magnetic field, this is the electrons. Okay, and when you apply the external magnetic field, atoms having your own magnetic field, and when two will interact, secondary magnetic field arises, and nucleus will be shielded by that. Okay, secondary magnetic field, and these all the electron then able to absorb the radio frequency. Okay, so it is the concept for that. Okay, so next we will talk about the chemical shift. So chemical shift. Okay, so chemical shift actually there, first of all we will talk about the reference compound will. Okay, so one is the mu, means frequency will be the reference compound, and one will be the frequency of your sample. So difference will be arises which will give your del value in megahertz. Okay, so tetramethylsilane, I think all of you aware from that. Tetramethylsilane mostly used, and it is the TMS, tetramethylsilane, and meets all the characteristics which will be required for the reference compound. Okay, and it is represented by del. Okay, so all the, if you see in this, I have also mentioned your deuterated solvent which required for your dissolution of your sample when you are going to take the NMR spectrum. Okay, so all the samples, all the solvents exist in deuterated form, and it is used for that. Okay, so we will talk about the chemical shift. Sorry for that. This one. So if you see here, aldehyde having this is the shielded region, this is the deshielded region. Okay, so I have in arrows, I have represented this. This is the shielding, this is the deshielding. Okay, so deshielding, all the CHO and acid or acid protons, this is the aromatic proton, will be arises in the deshielding region, while aliphatic protons appear in the shielded region. Okay, so on the chemical shift, there are some important factor involved in this. In this, you can also analyze that all the alcohol will be arises 4.0 to 9.0, acid arises from 10 to 12, aldehyde arises from 9 to 10. Okay, and some all the functional group I have mentioned here, so you can see. Okay, so all the compound which having electronegative atoms mostly arises in the deshielding region. Okay, one is that the effect of hydrogen bonding on the chemical shift I have mentioned in this. In this molecule, what happen here? These involve the intramolecular hydrogen bonding. Okay, so due to intramolecular hydrogen bonding, your protons appeared in lower field shift. Okay, so it will be appeared in lower, you can say in the shielded deshielded region. Okay, while in which this hydrogen bonding will intramolecular hydrogen will not present, it appeared in the deshielding region. Okay, so in this you can see the COH which will arises 12.5. so due to chlorine effect will be arises, and in this typical molecule it will appear in the 9.8 something like that. Okay, so okay, so it will be come in 12.6, but in this 9.8 region it will come. Okay, so in this if you see, this is the intramolecular, this is the actually enol ketoenol tautomerism which is present in this molecule, and it exists in 16% keto tautomer as well 84 point enol tautomer. If you want to suppose that any organic compound you are going to do NMR spectra, so your sample which you prepared for that, in the NMR tube it exists like that. When means external magnetic field applied, this sample in keto tautomer exists in 16%, 84% tautomer exist in enol form. Okay, so that's why there is a very toughest, you can say, determination for this compound. Okay, so your spectra will be arises for alpha beta unsaturated ketone. Okay, and in this if you see hydrogen bonding since present, so it will arises 14.5. Okay, hydrogen will be arising 14.5, which indicates that in this intramolecular hydrogen bonding is present. Okay, so thank you for watching this video, and in the next lecture we will talk about some basic concept, and we will solve the regarding the spectra, regarding NMR spectroscopy. We will actually solve some problems regarding this. Okay, so thank you for watching this video, and we will meet as soon as possible. Okay, so thank you for that.